Good day everyone, I am here to talk about our project for feedback and control systems entitled Design and Simulation of a Optical Mark Recognition, also called as OMR, for entrance examination and electoral system using MATLAB and Simulink. And now we are here in the dashboard page that allows us to configure any inputs to our OMR machine. So there are two modes. The first one would be the examination mode. It configures the algorithm to expect a 1 out of 4 multiple choice format. So it is A, B, C, D. The next one would be electoral mode. So it configures the algorithm to expect a 1 out of 2 candidate A versus candidate B format across multiple categories. So besides it would be the input console or the parameters. Here we can scale the environment like setting sample sizes and injecting physical constraints like stray ink density. So besides it also would be the active processing node. So it will be the brain of our system. So it represents our Raspberry Pi microcontroller, and here you can watch our Sugeno Fuzzy Logic algorithm actively calculating error rates and shifting the camera threshold in real time. The next one would be the error darkness or smudge factor. It dictates how dark a smudge or erase mark is. The next configurable input for the test benches, we have the random mode or the stress testing. The system generates completely random shading data, pixels darkness from 0 to 100 for every bubble. The next one would be the test cases mode, or also called profile testing. Instead of pure randomness, the system generates the data based on these specific student profiles. Profile 1 would be the perfect student. He shaded all the correct answers perfectly at 95% darkness. Profile 2, the eraser, so it shades the correct answer at 95% but leave a messy smudge based on our error darkness input on a wrong answer. So profile 3 would be the light shader. So this one shades very lightly, forcing the Sugeno algorithm to lower the threshold to catch it. Number 4 would be the blank or double mark. It leaves questions blank, or the student leaves questions blank or double shades them. So let's talk about the buttons. The first button would be the execution button or the run master OS script in our dashboard. So this is the primary trigger. Clicking this compiles the MATLAB workspace. It also initializes the plant or the mathematical model of the camera. It also builds the 3D Sugeno Fuzzy Logic brain and launches the Simulink hardware in the loop or HIL simulation. So below it would be the mathematical stability visualizers. We have the option and items analysis graphs, electoral tally graphs, and also the Root Locus, Nyquist, and Bode plot. The farther right, it would be our receipt section. So it tabulates the validated data into thermal receipts, and also it is based on the tally charts or the charts beside it. So now we will do some testing. The first test would be the electoral stress test. So we will now configure the parameters. So after we run the hardware in the loop simulation, we would see a theoretical stability graph. So as we look at the step response graph, we can see exactly how our Sugeno logic solved the problem. So as you can see on the electoral tally bar chart, we do still record invalid votes. That is for the voters who deliberately double shade. The next test would be the exam stress test. So we will now configure the parameters by setting the system mode to entrance exam mode. So same as the electoral mode, after we execute the hardware in the loop simulation, there would be a theoretical stability graph. As you can see in the item analysis bar chart, our invalid mark counts now only accurately reflects only for those students who intentionally double shaded. To conclude, we built a comprehensive test bench using MATLAB. By triggering the master OS script, we routed this simulation data through our Simulink architecture, allowing us to generate our item analysis graphs and mathematically prove our stability using Bode plot, Root Locus, before we ever touch the physical hardware.